Так, началась ли запись? Так, итого, значит, что, то есть мы можем начинать или можем начинать? Okay, well, let's begin. Anyway, where were we? So there's this lemma which says something about the kernel of the adjoint operator, and we want to apply it, but we don't know whether or not the orthogonal complement is the co-kernel of the operator itself. Now, let's see. Well, suppose we have a Bray-Hilbert space. Now, a vector subspace is complementable if W plus W orthogonal is the whole space. Now, example. If V is Hilbert, then a subspace is complementable if and only if it is closed. Which is more or less straightforward. Another example. In the Bray-Hilbert case, there are closed subspaces which aren't complementable. Let's take the space of all finite sequences of real numbers with a scalar product given by the sum of the products of the coordinates. And well, for example, let's take x inside L2 minus minus L2 finite. Now, is everyone familiar with L2? As a vector space, is just the set of all sequences of real numbers such that the sum of the squares converges. And on this vector space, there is a scalar product, and so on. Okay, so, let's take, for example, something which belongs to L2, but which isn't a finite sequence. For example, this one, or any other element would do. Now, let's take W equal X orthogonal in L2 intersected with V. Okay, so we'll take the orthogonal complement inside L2, inside the space of all sequences, and then intersect with V. What do we get? Well, we get something. And the something is closed because W is closed, being the intersection of the orthogonal complement with V. So this is closed in V. But it's not complementable because the orthogonal complement of this subspace inside V is 0. If we have an element inside the orthogonal complement of W in V, this element also belongs to the orthogonal complement of W in L2. Why? Well, because V is dense in L2. But the orthogonal complement of V in L2 is spanned by X, and X does not belong to V. So there are non-complementable subspaces. Now there is a corollary of this lemma, which basically says that for elliptic operators, we once we have proved that elliptic operators have a closed image and their Fredholm, we will be able to claim that the index of the joint operator is minus the index of the operator itself. So corollary. Of what? Of this lemma. Suppose I have a Fredholm operator from V1 to V2, where V1 and V2 are both Bray-Hilbert spaces. And suppose the joint operator exists, is Fredholm, and the image of A and the image of A star are complementable. Then the index of the joint operator is minus the index of the operator itself. And we basically use this lemma to see that so if, for example, if the image of A is complementable, then the dimension of the orthogonal complement is precisely the codimension of the image. Of the space itself. Now, which is the same as the co-kernel. So if so, this subspace is isomorphic to the co-kernel of A if the image is complementable. And we'll see that for elliptic operators, this will indeed be the case. So supposing this is complementable, the co-kernel of the operator A has the same dimension as the kernel of A upper star. And vice versa, the kernel of A has the same dimension as the co-kernel of the A upper star, and we get this equality. Are there any questions? So it often happens, and well, especially in examples we'll be interested in, that the kernel of the joint operator is the same as the kernel of the operator itself. Sorry, not the kernel. The index of the joint operator is the same as the index of the operator itself times minus 1. Okay, are there any questions? Well, now I would like to talk a little about the general theory of elliptic operators, and and then maybe we'll talk a little about the Hodge decomposition. Okay. An alternative would be to talk about the Hodge decomposition next time and to discuss characteristic classes. So what do we want to do?
Maybe characteristic classes.
Characteristic classes, okay. But then has anyone taken a look at the problems from the first problem sheet? Okay, well then. What does it say? Problems from Math in Moscow. Well, yes, it's something very similar. Let's assume it's the same. Well, there might be a few typos here, but it's essentially the same as the one we had in 2019. So yes, let's assume it's the right one. Okay, so characteristic classes. We'll mainly be interested in the Chern classes, but there is a parallel theory of the Stiefel-Whitney classes, and there is also the Euler class, which is very important. Okay, now are there any? Basically, all questions from the first problem sheet should be straightforward. But if they're not, let's talk about those which are less straightforward than the rest. Okay. Are there any questions that you don't know how to do from the first problem sheet?
Я лично вообще почти ничего не знаю. Ну, как бы я с классом Черна сталкивался только в алгебрическом контексте, и то только с первым.
Ну, там где первый, там же и второй. И третий, и четвертый. Well, let's see. So, well, the first Chern class is let's define the first Chern class for line bundles. And for line bundles, we basically we do we do the following thing. We take we know that line bundles are classified by maps into CP infinity. Now, does this make any sense at all? Well, let's see. Volodya, does this make any sense at all?
It makes some sense. Yes,
Some sense. Well, let's remember the classification theorem for vector bundles. And there are, well, let's not worry about too general, about topological spaces which are too general to come up in practice. Let's say we're only interested in CW complexes. Now, we want to classify vector bundles. Now, to begin with, does everyone understand what okay, let's start with finite Grossmanians. Is everyone familiar with finite Grossmanian manifolds? Now, okay, so we have the Grossmanian manifold of R planes in Cn. Now, so far so good. And now, and by the way, there are lots of ways to define a topology on this space, and they're all equivalent. What's the simplest one, by the way? Well, yes, that's one way. For example, we could take well, UN acts transitively on the set of all R planes. So we could and the stabilizer of an R plane is what? Is UR cross U n minus R. And we have this this isomorphism. Is there another way to topologize the space?
We can directly cover this space by maps.
Yes, there is a way to glue this using several copies of the affine space C to the power R times n minus R. And another way would be to take the unit sphere in Cn and parameterize all intersections of R planes with the unit sphere. Now, if I intersect an R plane with the unit sphere, I get a compact subset of the unit sphere. And there is the Hausdorff metric on the set of all compact subsets of a compact metric space, and we could take the topology induced by this metric, which is in a sense the most straightforward way to topologize the space. Anyway, because Anyway, everyone's familiar with this. Now let's go one step further. Let's take GR.
Are we working only over C?
No, we could put R here, and more generally any field. And maybe.
It must be not only about here, but about generally.
Generally, we want to work with characteristic classes of complex vector bundles. Because ultimately, because the complex K theory is more computable than the real K theory. This is the real reason we want complex vector bundles, not real vector bundles. But for real vector bundles, everything works in more or less the same way. But there are some of the answers are completely parallel to those in the complex case. Some are more complicated and so on. But we'll mainly be interested in complex vector bundles and hence Cn. Okay, now I want to take the limit as n goes to infinity. Now, does this make any sense? Basically, I take the direct limit on the level of sets and then take the direct limit topology. A subset of the direct limit is closed if and only if its intersection with each finite space is closed. Okay, so this is the infinite Grossmanian. Now. Yes, so as a set, yes. So this is the same as the set of all R planes in C infinity, where C infinity is the direct limit of Cn's. Okay, now we have the tautological vector bundle. Over each of these Grossmanians, there is a tautological vector bundle of rank R. Does everyone understand what this bundle is?
Is this letter R?
This one, yes. Do we or do we not need to review the tautological vector bundles? Well, let me say this without writing it down. Elements of GR are R planes. Now, I I could consider the set of all couples a plane, a vector in this plane. And this this thing projects into GR, and the fiber is the fiber over a plane is the plane itself. And one can prove that this triple is in fact a vector bundle, and this vector bundle is called the tautological vector bundle. Now, if we need to talk about this in more detail, please let me know. Now, the classification theorem says the following thing. Suppose X is a CW complex. And suppose E is a vector bundle, complex vector bundle. Then E is isomorphic to F minus 1 gamma rank E for some F from X to G rank E. Okay, so every vector bundle is induced by from the tautological vector bundle using some continuous map. Here we consider continuous line bundles, continuous vector bundles of an arbitrary rank. Okay, so every vector bundle is induced from the tautological bundle via some continuous map. Moreover, two continuous maps induce the same or isomorphic bundles if and only if they are homotopic. And it's well, it's not very hard to prove this theorem. For example, there's one source which I recommend. It's a book by Miller and Stashev. Which is called characteristic classes, and probably you're all familiar with it, but just in case, here it is. Okay, now now we return to line bundles. Well, if R is 1, then GR is just CP r minus 1, and GR of Cn is CP n minus 1, and GR is G1 CP infinity. We have this diagram. Every line bundle comes from the tautological line bundle over CP infinity.
What is E of gamma 1?
The total space.
By the way, I guess this is a stupid question, but I mean, it's different from the classifying spaces of UN, right? Because, I mean, gamma R is not contractible. But I mean, in your notes, you said that we denote gamma R by, I mean, E UN. So it's not like it's true. Right? Is it? I mean, is it contractible?
What?
Gamma R.
Gamma R. Gamma R is a vector bundle. In particular, there's the total space, the base, and so on. So there are two different things. There is E-UN, which is contractible, and there is E of gamma, E of something. They're not the same thing. They're different.
But I mean, in your notes, you said they are the same thing. So maybe, I mean, this wasn't.
Does it? Does it? Well, let's have a look.
Yes, here. You said that here we call this. Oh no, you called the BM, not TU. Okay, I messed up with the BM.
Okay, so B-O-M.
Yeah,
Yes, another way to another basically another notation for this space is B-U-R. Now, what does this mean? Well, this means the classifying space of the group UR. We'll need to talk about this, but let's do this later.
So it doesn't mean that, I mean, it is the, I mean, the classifying space of U R. No, it's not. It's just notation.
No, sorry. Yes. Hold on. This one is the classifying space. This one isn't. The Grossmanian is the same as the classifying space of the unitary group, up to homotopy, and so on. We'll need to talk about those, but maybe let's do this later. Okay, so E of a vector bundle is how we denote the total space of this vector bundle. Okay, so in particular, we have this diagram, and we are now able to define the first Chern class. How do we do this? We take the classifying map, which induces the given line bundle, and we take the positive generator of the cohomology. The positive generator of what? Of H2 of CP infinity. I take the positive generator, I pull it back, using f, and then I get something. And then I multiply it by minus 1. It's just a matter of convention, really. There's no deep reason for this minus 1 to be there. The not so deep reason is that the positive generator is the first Chern class of the co-tot. I'll write it down, but it's not really very important. So on CPN, there are two famous vector bundles. There's gamma 1, which is the tautological bundle, we've just seen it, and there is O of 1, which is familiar from algebraic geometry. They're not the same. They're the dual of one another. So gamma 1 is in fact O of minus 1. Now, if we want the first Chern class of O of 1 to be positive, the first Chern class of gamma 1 will be negative, and vice versa.
I have a question.
Sure.
What do okay. I thought that we are talking about arbitrary x, but we're talking about En.
I'm trying to explain where this minus comes from.
What is O of 1?
O of 1. Okay, does anyone know what O of 1 is? This is a bundle of which is basically familiar from algebraic geometry. Now, is there anyone here who did some course in algebraic geometry? Okay, then can you explain to Vladimir what O of 1 is?
Maybe we should look at global sections. Global sections of O of n are homogeneous polynomials of some variables of degree n.
Well, it's not really a definition because there are many vector bundles which just happen to have the same or isomorphic spaces of sections. Now, okay, so let's try to remember. There is another interpretation in terms of hyperplanes, hyperplane section bundle. No?
So divisors. Okay, if we take to any subvariety of codimension 1, or even for any linear combinations of subvarieties of codimension 1, to this combination we can, using this combination we can define some line bundle. And conversely, if we have a line bundle, we can take a rational section of this bundle, and it will have some zeros and some poles. And so we can take zeros with plus sign and false with minus sign. And this will be a combination, a linear combination of closed varieties of dimension 1. So this is called a divisor. This is a bijection between actually classes of divisors and line bundles. And if we take as a divisor a hyperplane in projective space, then the corresponding line bundle is O of 1. In other words, O of 1 have a section with no poles and zeros and 0 on one hyperplane.
Okay, so in other words, let's think of CPN as the set of all hyperplanes, not lines, hyperplanes, which we're allowed to do because they're isomorphic. Okay, now let's, for each hyperplane, let's take all linear polynomials, linear homogeneous polynomials, which are 0 at each point of this hyperplane. There is one-dimensional family of those. Now, if I take the set of all couples, a hyperplane, a one-dimensional family of polynomials which have degree 1 are homogeneous and are 0 on this hyperplane, then I get the total space of O of 1. Now there is one thing which is pretty which I think one can prove without any okay, just to see the difference between O of 1 and O of minus 1. O of 1 has sections. O of minus 1 does not have sections. Well, let's prove it. Let's prove this. It's not really very difficult. Sections are holomorphic sections. Okay, so O of 1. Let's take CP1. Let's not come for simplicity. Let's not overcomplicate things. The total space. Now I'm using my notation E. The total space of O of 1, what is it? It's the set of all triples x1, x0, x1, f, such that f is homogeneous of degree 1. So I take CP1, x0, x1, f hold on, here, okay, minus 1. No? No. Let's. This is a quotient, not a subspace. Okay. Okay. So the total space is. Okay, let me think about how to. So the fiber is the fiber of O1 is the quotient of C3 by something not a subspace. Okay, I'm starting to use bad notation, but I can't think of anything else. F belongs to the quotient of C3. So here C3 is the space of all polynomials of degree hold on, why is it 3? No, 2, yes. So here C2 is the space of all homogeneous degree 1 polynomials in x0, x1, and we quotient out the space of all polynomials which are 0 on the line spanned by x0, x1. So this is the total space of O of 1, and now the total space of gamma 1. And it's clear from this description that O of 1 has as many sections as there are elements in this space. We just take any element here and take its image in the quotient space, and we get a section. Now,
It vanishes at 1 point.
which will vanish at exactly 1 point, unless it's identically 0. Okay, now what is the total space of the tautological bundle? Again, I'm using bad notation. x0, x1 is an element of CP1. And I take for each x0, x1, the fiber over it will be the set of all AB, which belong to this line, which in practice means we need to fix a representative for x0, x1, and then we take the set of all multiples of this representative. Now, this bundle has sections. This does not have sections. Is this clear?
Yes, but I think the fibers should be dual canonically to each other.
Yes, the fibers should be dual. What's the duality? Well, if I have a polynomial, I can substitute A and B for x0, x1. Now, the the claim is this will give me the pairing between these two vector bundles. Now, for example, if I take something which is 0 on this line, I get 0, which is what I'm expected, which is what I'm supposed to get in this case. Okay, now let's see that this. Let's see why this bundle doesn't have sections. Holomorphic sections. There are obviously lots of smooth sections, but there aren't any holomorphic sections. Well, suppose there is a holomorphic section. Now, what does this mean? Well, this means there is a map from CP1 to C2. This total space lives inside CP1 cross C2. So a holomorphic section would be a map from CP1 to CP1 cross C2, such that when we compose back with the projection, we get the identity. Now, I know a theorem from either basic algebraic geometry or or basic complex analysis. There aren't any non-zero functions on CP1. So this map takes any x0, x1 to x0, x1, and then some a naught, b naught, which is a fixed element. Why? Because CP1 has no holomorphic functions other than constants. So, okay. Now, so for example, so this element is fixed, and x0, x1 is arbitrary. So it often happens that this fixed element will not be on the line spanned by x0, x1. And so this bundle, as opposed to this bundle, has no holomorphic sections, which is why some people think that this bundle is better. And since it's better, the first Chern class of this bundle is defined to be positive, and the Chern class of the other one is defined to be negative. Well, this is this is my understanding of why we have this this sign issue here. But anyway, that doesn't really matter. We have if we have the classifying map, we are able to define the if we have a classifying map, we're able to define the first Chern class for line bundles is just by taking the pullback and then multiplying. Or we could take a plus here and take the negative generator. The result would be the same. Okay. Does everyone understand how the first Chern class works for line bundles, at least on the level of definition?
What are the second homology of CP infinity?
Well, it's another good question. The cohomology of CP infinity. We have an isomorphism. The cohomology of CP infinity is the same as the ring of polynomials in one variable, which has degree 2. Now, we could take this variable to be either the positive generator or the negative generator. Basically, the results would be the same up to multiplying the generator by plus minus 1. Now, okay, what I was supposed to, so we have this isomorphism, and there are many ways to prove it. For example, one could use the CW structure, or well, there is a preferred CW structure on CP infinity, and it's one way to prove this isomorphism, and there are many others. Okay, now does this definition make sense now? Well, okay. So far so good. Now we need to prove that the first Chern class has some nice properties, and in particular we want to prove that the C1 of L1 tensor L2 is C1 L1 plus C1 L2, and likewise C1 L dual is minus C1 of L, where L, L1, L2 are line bundles. Okay, and there's an exercise somewhere in the first problem sheet which more or less explains how to prove both these formulas. Okay, well, let's have a look at this exercise and see whether or not we understand how to do it. Could be on the second page.
Question 2.
Question 2. Well, okay.
Question 1 is about functoriality.
Functoriality. Well, functoriality is more or less clear. If we pull everything back, the pullbacks are functorial. Now let's.
I have a question.
Sure.
There's a statement in the end of the hint to this question, which is not quite clear to me. So it says that if you are given classifying maps from X to CP infinity for E1 and E2, then the tensor product is obtained by pulling back gamma under the map from X to the product CP infinity with itself. So
Well, so we have two classifying maps from X to CP infinity and another one from X to CP infinity. Well, let's. Let's take the product of these, and we get a map from X to CP infinity cross CP infinity. Just by taking an element here to the couple the image under the first map, the image under the second map. Okay, so now over CP infinity we have the bundle gamma 1 cross gamma 1. What does this mean? Well, this means I pull gamma 1, pull back gamma 1 from the first factor, from the second factor, and then take the tensor product. Okay, now this is a an honest vector line bundle over the product CP infinity. Now I want to okay. Now if I take the pullback of this bundle, I get L1 tensor L2 on X. So if gamma 1 pulls back to L1 and under the first map, and gamma 1 pulls back to L2 under the second map, then when I take this map, it pulls back to the bundle pulls back to the tensor product. Ну, давайте посмотрим. Куда еще? Ну, значит, давайте смотреть. Значит, у меня I have a map from this space to this space. And I have a vector. I have a line bundle here, which is a tensor product. Tensor products pull back to tensor products. So let's see where the factors pull back, and then take tensor product here. Okay, so I have this thing is a tensor product of two bundles on this space. Let me take the first bundle. This first bundle is in fact the pullback of gamma 1 on this factor. Okay, so what I need to do, in fact, is to take this map and then forget about the second factor. And this is exactly the classifying map for the first vector bundle, line bundle L1. Does this make sense?
Yes.
Okay, so now we want to calculate. We want to calculate the well. In order to calculate the Chern class of this bundle, we need to take the cohomology map induced by. We need to calculate the cohomology map induced by this map. Okay, now but moreover, we're only interested in the map of the second cohomology. What's the second cohomology of CP infinity cross CP infinity?
All cohomology is a tensor product of Z of A and Z of B. I don't know.
And what is A and what is B?
A is this A, and we need another method.
Okay, yes. So basically, CP infinity has no torsion, and nothing fancy happens. We just take the tensor product of the two copies. But in particular, H2, which is all we're interested in, is generated by C1 of gamma 1, 1, and C1 of gamma 1, 2. Basically, it's generated by C1 of this bundle and C1 of this bundle. Well, now I need to calculate where these two classes go under the induced map. Let me take each of these individually. The first one, this one is pulled back from this factor. So it goes back to the Chern class of this one, and the second one goes back to the Chern class of this one, and I've calculated the pullback in cohomology. Okay, now I need to calculate the Chern class of this bundle in terms of the individual factors. And by the way, what do the hints say?
We need to fix an element x0 in CP infinity.
Okay. Well, let's think a little. So we have this vector bundle, no, this line bundle, and we know where which bundle it pulls back to, but we want to know that we want to calculate its Chern class, and we want to we want to prove that the Chern class of this is the sum of these Chern classes. Okay, any ideas how to do this? Well, CP infinity cross CP infinity is a relatively simple space. Okay, we have this vector bundle, line bundle. Let's restrict it to this factor, meaning let's fix an element here and consider a copy of CP infinity cross a fixed element here. The bundle becomes gamma 1 on this copy. And the Chern class, the cohomology map is what we think it is. Basically, I have this these two elements which form an additive basis of H2. I have the Chern class. I want to calculate the coefficients of the Chern class in this basis. I restrict to this factor, and I get both coefficients. Значит, что произошло? Значит, есть аддитивный базис. Давайте его назовем как-нибудь. А можем не называть, можем просто представить себе, что это аддитивный базис. Значит, и у меня есть класс Черна вот этого расслоения, который я хочу посчитать. Я хочу посчитать его коэффициенты. Ну что я делаю? Я ограничиваю на эту CP1, в смысле на эту CP бесконечность, на эту CP бесконечность. Значит, одна мне дает один коэффициент, другая другой коэффициент. Ну, а больше коэффициентов нету, потому что у меня, значит, вот здесь вот все двумерное, и значит, это все очень сильно упрощает. Значит, ответ. Значит, результат, что класс Черна вот этого будет, значит, суммой класс Черна вот, от вот этого потянутого сюда и класс Черна от вот этого потянутого сюда с помощью другой проекции. Сумму, вот именно сумма. Okay, so I think we've run over time, or maybe not yet, but we're about to. Does this make any sense? And by the way, well, it's probably better late than never. I know Vladimir, I know Saman. What's your name? Leonid, and what's yours? Nina, хорошо. Очень приятно. Well, as I said, better late than never. And I'm Alexei, by the way. Anyhow, do we all agree that we have this formula, which basically implies this formula? Нина, понятно ли, откуда получается вот эта штука? Ну, значит, смотрите, вот, значит, вот у нас есть CP бесконечность, там такое расслоение, которое мы сейчас обозначили как гамма-1, там крестик в квадратике гамма-1. Значит, потянули гамма-1 значит, с помощью одной проекции, другой проекции тензорно перемножили. Вот у нас есть такое расслоение, оно живет над CP бесконечность, крест CP бесконечность. Вот, дальше у меня есть отображение из X вот в это произведение. Хорошо, значит, дальше спрашивается, а куда тянется назад вот это расслоение при таком отображении? Если, значит, при вот, отображении в эту CP бесконечность тянется в L1, а в эту, значит, в L2. Вот у меня есть два отображения. Из X, значит, в эту CP бесконечность, значит, при этом отображение гамма-1 тянется назад в L1. И аналогично, из X в эту CP бесконечность. И там вот при втором гамма-1 тянется назад в L2. Вот теперь, значит, я хочу понять, а куда тянется назад вот это. Ну, значит, поскольку вот это тензорное произведение, мы должны потянуть назад каждый из множителей отдельности, в отдельности. Ну, тянем. Значит, первый, значит, я утверждаю, что первый тянется назад в L1, а второй в L2. Вот, понятно ли это? Хорошо, значит, итого у нас вот есть такое расслоение, которое там тянется назад туда, куда нужно. Мы знаем, что класс черно функториальный, поэтому нам достаточно посчитать класс черно вот этого, и тогда мы все посчитаем. Давайте посчитаем класс черно вот этого. Значит, но опять же мы пользуемся тем, что класс черно функториальный. Значит, и еще мы пользуемся тем, что класс черно живет вот в этом вот, значит, вот в этой подгруппе, которая на самом деле свободна Абелева, там ранга 2. Ну, у нее есть базис. Значит, базис, он тоже состоит из классов черно. Класс черно, значит, потянутого, класс черно, там, гамма-1 потянутого, значит, при одной проекции, класс черно, гамма-1 потянутый при другой проекции. Ну вот, а у меня есть вот этот вот еще неизвестный класс черно, вот это вот расслоение. Я его как-то запишу по базису. Вот, значит, дальше захочу вычислить коэффициенты. Что я делаю? Значит, я значит, ограничиваю на... То есть я фиксирую какой-то элемент здесь, значит, рассматриваю соответствующую копию ЦП бесконечности. Значит, значит, дальше смотрю, как отображаются элементы базиса. Для элемента базиса там один 0, другой соответствующий элемент базиса для ЦП бесконечности. И это мне дает первый коэффициент. Ну, там оказывается, что он равен единице, потому что там, ну, просто обратно получается то же самое расслоение. И, значит, аналогично второй коэффициент. Да, значит, итого, значит, я доказал, что вот значит, C1 от гамма-1 крестик квадратики гамма-1, это равняется. Значит, давайте так, значит, P1 со звездочкой C1 гамма-1 плюс P2 со звездочкой. Ну, да, вот, хорошо, давайте сейчас что-нибудь сотрем, напишем где-нибудь еще. Давайте вот здесь напишем. Что мы еще доказываем? So we have CP infinity. Yeah, that's not it. CP infinity cross CP infinity. And CP infinity. We have two projections. Let's call them P1, P2. We have so we have C1 gamma 1 box cross gamma 1 is equal to C1 of the first pullback okay, let me put it like this, and plus P2 C1 gamma 1. So we have this formula. These two elements are the elements of the basis for H2. And I calculate both coefficients. I get 1, so I get this formula. Now we want to. Now we know this this class, and we need to apply this formula. We need to know where these two classes go under the pullback induced by this map. Let's consider them. Let's consider each of them individually. And the first one goes to the Chern class of the first bundle, and the second one goes to the Chern class of the second bundle. Нин, я предлагаю чуть-чуть там попробовать это все продумать дома, если там по-прежнему... В общем, если это не там останутся какие-то таинственные моменты, давайте там обсудим в следующий раз. Okay, and basically using the same sort of argument, we can prove the second identity. Basically, for line bundles, all we need to know to define the Chern classes is the cohomology of CP infinity, nothing else. Okay, so I suggest we probably need to stop. Another suggestion. Let's please have a look at the next few exercises. The purpose of the first problem sheet is to explain how to define the Chern classes and prove the basic property of the Whitney formula. And then we'll need to use those to calculate the index of various operators. Are there any questions?
Yes. I mean, maybe it's not relevant, but I mean the first, in the beginning of the lecture, you defined the elliptical complexes. I mean, does that? I mean, it has a homology. I mean, does that give us something interesting?
Usually yes, and basically we'll see. For example, in the de Rham case, this gives the de Rham cohomology, and in some other cases it gives other kind of cohomology, such as the cohomology of coherent sheaves, for example, and so on. Are there any more questions? Okay, then let's probably stop the recording and